Welcome to Topic 7, History and Structure of the Universe. Here's just a little funny cartoon. Radio telescopes are another type of telescope that detects and records radio waves coming from stars and other celestial objects. It consists of a radio receiver with an antenna fixed on a wide bowl-shaped reflector that collects radio waves. Why do we need such a large bowl? Because radio waves have very long wavelengths, and you need a very large reflector to reflect it into a radio detector. The position of the 27 radio telescopes in New Mexico's very large array can be adjusted to measure wavelengths from distant objects in multiple configurations, so they can adjust it depending on what they're looking at. The massive radio telescope in Puerto Rico can detect the source of extremely distant radio waves, so they can use it to look at objects that are very far away from Earth. Telescopes such as the Hubble satellites and space probes all use and detect a range of electromagnetic radiation such as infrared, ultraviolet, visible light, microwaves, and radio waves. What are some benefits of using such expensive technology? It allows us to determine the temperature, chemical composition, geology, and atmospheric gases of other planets, and stars. It allows us to locate supernovas, pulsars, neutron stars, and black holes. What planets are similar to Earth, which are habitable? It allows us to understand the history of the Earth better. What are some concerns regarding this technology? It can be very costly, and the materials used may be very toxic to people on Earth. What penetrates the Earth's atmosphere? If you'll notice by this graph, the only thing that actually hits the surface of the Earth are visible light, infrared, and radio waves. The other ones, gamma rays, X-rays, and ultraviolet rays, don't hit the Earth. Because high energy rays come from the hottest stars, we need telescopes above the Earth's surface to get a better picture of the types of radiation that these stars give off. Spectrum can tell us about the composition and temperature of stars. Astronomers collect EMR with telescopes. EMR, remember, consists of light and other radiation. It's separated into spectrums of wavelengths, or if you're talking about visible light, into colors. White light can be passed through a prism or a diffraction grating to separate wavelengths or colors of light. A spectrometer is used to measure wavelengths of light. A spectrometer is a simple device that's made from cutting parallel lines on a transparent acetate sheet and inserting a prism or diffraction grating into this tube. There are three types of spectra. The first are a continuous spectra, where all the colors of the wavelengths are present. The second is an emission spectra, where there are a discrete number of colors or wavelengths present. And the third is an absorption spectra, or a dark line spectra, where all the colors are present except the discrete number in which are absent or absorbed. The colors missing from an absorption spectra are equal to the colors emitted from an emission spectra. This is the absorption spectra, emission spectra, and continuous spectra of the Sun. It shows a surface temperature of 6,000 degrees Celsius, and it shows that helium, hydrogen, and 70 other elements are present. Part A is a continuous spectra, where it shows all of the light emitted. If you put cool gas in front of the light from the Sun, you get an absorption spectra, so you have all the colors except the black lines that are missing. And if you put low density gas heated to incandescence, the only light gets through are those emitted, so you see the dark line or the banding. So again, just the light as visible through the eye creates a continuous spectrum. If you put hot gas in front of the light, the object emitting light, you get emission line spectrum, and if you put cold gas in front of the light bulb or the object emitting light, you get an absorption line spectrum. Notice that the emission line and the absorption line, the dark bands that are missing from the absorption line spectrum, are present in the emission line spectrum. Spectral analysis. Each element has a unique absorption spectrum or a pattern of lines. We can look at the absorption spectrum from a star so as to tell us what elements make up the atmosphere of the star. We can compare the unknown spectrum with the spectra of known elements. So here's an unknown star, and here is the absorption the absorption spectrum for helium. There's chromium and there's barium. So this matches helium. It does not match chromium and it does not match barium. So it has lines that are similar to helium but not chromium or barium. What about the temperature of the star? High temperature stars have fewer lines, so they have less energy absorption. Spectroscopy or spectroscopy is also used to determine the thickness of the ozone layer. UV that is reflected back to satellites is used to produce absorption spectra. The rainbow is a natural spectrum caused by the refraction and reflection of sunlight through raindrops, and it shows that sunlight consists of a continuous run, or a continuum, of colors from red to violet. Note the fainter outer bow caused by the double reflections inside the raindrops. So you can see a double rainbow there. How did we find out that the universe is expanding? So we studied the Doppler effect and spectroscopy. The Doppler effect affects sound, light, and other electromagnetic radiation waves. This can be explained why the pitch of a siren drops as the ambulance passes you. Wavelength shifts as the ambulance approaches. Wavelength of a star's light also shifts as it moves towards or away from the Earth. The siren from a stationary police car will sound the same at A and B because the frequency is equal, right? So it's not moving and they're equal distance away, so it'll sound the same. If it's moving if it's moving towards B and away from A, it'll sound louder at B than it is at A because it's moving towards it and it's closer. So those sound waves are being bunched. So B is a higher frequency. So, as it's moving away from this guy and towards this guy, the sound waves get bunched together. It'll sound louder as it comes towards you and fainter as it moves away. We've all heard that before. So as it moves away, it's longer wavelengths and a low frequency. As it moves towards you, it's higher wavelengths, or smaller wavelengths and a higher frequency. The Doppler effect in stars. The Doppler effect is of intense interest to astronomers who use the information about the shift in frequency of radio or electromagnetic waves produced by moving stars in our galaxy and beyond in order to derive information about those stars and galaxies. The belief that the universe is expanding is based in part upon observations of electromagnetic waves emitted by stars in distant galaxies. Furthermore, specific information about stars within galaxies can be determined by application of the Doppler effect. The expanding universe increases in actual volume with time and decreases in density. This is the Big Bang theory. The steady-state theory proposes that new matter is formed which pushes the galaxies farther apart, keeping the density of the universe constant. Recall, red light has a low frequency and blue light has a high frequency. If an object is moving towards you, the frequency is higher, so it would be blue. And away from you, the frequency is lower, so it would look red. Galaxies are clusters of stars which typically rotate around some center point of mass. If the star is rotating in its cluster in a direction which is away from the Earth, the EMR will have a lower frequency, so it will be shifted towards the red. The lower frequency light is red, and thus the stars would appear to be red or have a red shift. Recall, red light has a low frequency and blue light has a high frequency, and if an object is moving towards you, the frequency is higher, and away from you, the frequency is lower. If the star is rotating in its cluster in a direction which is towards the Earth, the electromagnetic radiation emission would have a higher frequency. A higher frequency light is blue light, and thus the stars would appear to be blue or have a blue shift. Redshift means shift to longer wavelengths because red is the longest optical wavelength. So long and red mean moving away from you. Short and blue mean moving towards you. Light from an object moving away from us shifts to longer wavelengths. The greater the redshift, the faster the source is moving away from us. What we found: no matter what galaxy we obtained electromagnetic radiation from, all spectroscopes were red-shifted. It means that the universe is expanding at a constant rate.